introduction to live, neutral and protective Earth, and why we use isolation transformers. Here we will consider a very simple power grid. This is the medium voltage side, which is up to a few kilovolts, and this is the 230 volts which we have at home. So this is the transformer, which is typically located at a transformer station or outside the building somewhere. Typically you don't get to see this transformer, you only see the 230 volts which come into the building. So at this point we have those two wires and they are completely interchangeable. There's nothing special about the top or the bottom wire, and there's no way to distinguish them. As long as you have both wires, you can get 230 volts power. Since it's AC, of course it has to be AC, otherwise it wouldn't go through the transformer. There is no plus or minus. It's just two wires carrying AC current. So why do we need to name them differently? Also, this example here will only take single-phase power supply into account. We're not going to three-phase power, which will be a separate video. Okay, to those two wires, we now add a third one, which is a grounding wire or earthing wire. And this wire, this part here, that's literally a rod of a couple of meters length, which is rammed into the earth somewhere. And that connects this wire directly to earth. And we tie this wire to one of those coming from the transformer. And now there's a difference between those two, because this one will be held at earth potential, and this is why we give those wires separate names. This one is live, this one is neutral, and this one is protective earth. And now you may ask yourself, why do we even have a separate neutral and protective earth wire? Because as we can see here, they are at the same potential, and having two wires would just be a waste of copper. Well, it would be a waste of copper, but we use a separate device in here, which is an RCD or GFCI. RCD and GFI or GFCI, they're the same thing. One is just the UK name and the other one is the US name. And what this device does is it monitors the current going through here and through here, and it checks whether the current is exactly the same. It really has to be very close, up to only a few milliamps. And if there's too much of a difference between power going through here and power coming back there, then the device will trip and open up the circuit. And this is why we have this separate wire here, because this is where we draw the power from. And if anything else comes back through the earth, either through the earth itself or through the PE wire, then this will indicate a fault condition, and we will see this later in the video. Let's add a very simple lighting circuit to this. We put in a light bulb, and the light bulb is switched with a switch, and the switch switches the live wire. Power goes through live, through the switch, through the light bulb, and back to neutral. We switch it on and nothing happens because the light bulb is broken. Okay, we switch it back off and we have some guy take out the broken light bulb. And of course, if you're standing on the ground, you're electrically connected to it. So we've drawn this in here. And now this very clumsy guy, when putting in the new light bulb, accidentally touches this wire here. Well, nothing will happen because the switch is off. So that's very important. When you change light bulbs, make sure that the lights are switched off before you touch the light socket. And he also touches the other end of the light socket, which will now be directly connected to the neutral wire, directly to the mains wire here. But this is not dangerous because the neutral wire is at the same potential as the earth. So no power can flow anywhere. This is totally safe. We put in the new light bulb and switch it on. And now we can see power flowing through live, through the switch, through the bulb, back through neutral and back into the transformer. Works as designed. Let's turn it off and add another lighting circuit. But this lighting circuit is improperly designed because here the switch doesn't switch the live wire, it switches the neutral wire. Well, technically it doesn't really matter which side is switched as long as the circuit is either closed or opened. So this will work just as well as the other circuit. But there's a problem. Yeah, the light bulb is broken again, so we get the guy to fix it. So clumsy guy takes out the light bulb, and when putting in the new one, he accidentally touches this wire. And now this one is directly connected to the live wire, so power will flow through the live wire, through here, through his body, through the heart, very dangerous, through the feet, into the ground, and back through the ground somewhere to neutral and into the transformer. And this is very dangerous. But what we can see in this circuit is now power won't flow through the neutral wire, but it'll flow through the earth. So the RCD will see that power goes that way, but it's not coming back through the path where it should be coming back. And when this is above a certain limit, it'll trip and hopefully protect this guy's life here. Hopefully. So the RCD will open, there will be no power in the system anymore, and yeah, hopefully he won't die. Okay, let's assume he still lives, puts in a new light bulb, and we switch it on. And yes, I haven't drawn those orange power wires, but we can see the light bulbs works just as well, because it doesn't really matter where the circuit is interrupted as long as it's interrupted. But obviously this one is wired wrong, so don't do this because it's dangerous. Let's move this one aside a little bit. And we plug in another device. This is a bit more complicated device. It's a function generator. So this function generator is connected to live and neutral as well. It has its internal power supply, which converts it to a low voltage, also electrically isolates it from the mains wire to make it safe to touch. But this function generator, it has a metal case. And a device having a metal case needs to be grounded or earthed. And this is why the metal case is connected to earth, and we will see later why it's important to have this earthing of metal cases. But not only that, the output here is a BNC plug, and the outside of the BNC plug is metal as well. So the metal of the BNC plug touches the metal case. So this means that the outside of the BNC connector, the shielding, is connected to the case as well. This one on the back side, this one on the front side, but they're both connected to the same case. Yeah, let's add another device. This other device is an oscilloscope. And the oscilloscope has the same kind of problem with the case. The case is made of metal, so it needs to be earthed. And it has also BNC plugs on the front, this time for input. And this means also that the outside or the shielding of the BNC plug is connected to the same case. So for a quick demonstration, let's wire those together. Let's take one cable and plug them together. We have the function generator generate a simple triangle wave. And if we look at this on the oscilloscope, we will see the oscilloscope shows exactly the same triangle wave, exactly as it should. But now let's add one more component to the circuit. Let's add a little battery between the function generator and the oscilloscope. And the battery, we put it in here in the signal wire. This will shift the triangle wave up a little bit. It will shift it up by the voltage of the battery because it just adds an offset to the voltage coming from here. And this also works as it should. But what happens if we take this battery and don't put it in the signal wire, but instead we put it here between the two parts of the ground wire, like this? And remember, this doesn't just have to be a simple battery, it could be any more complicated circuit, but in this case we'll just take a basic battery which would shift the output of the oscilloscope now in the opposite direction, but oh look, it doesn't shift it at all, it just has the same wave as the input. So why doesn't it work? You won't see the oscilloscope output move, but you will see something else. You will realize that the battery suddenly starts getting very hot. And the reason is because there's a short circuit. And the short circuit is through the case, through here, through the case of the oscilloscope, through the earthing wire, over here, through the case of the function generator, and through the other, and again through the BNC plug. So this short here will really be through the cases of the two devices, through the earth wire in the power grid. This will short the battery, and the battery will get very hot, and probably also the wires connecting all this will get very hot. This is very bad. This is not what we want. Again, battery is just a placeholder for a more complicated circuit, but what we really want is we want to be able to have the potential of this ground plug be somewhere else than the potential of that ground plug. But having those tied together through the earthing makes this impossible. So a very primitive solution would be, the earthing wire is the problem. Well, let's just get rid of one of the earthing wires. Let's just open this up, maybe by sticking some tape on the outside of the plug, or just snipping off the earth wire somewhere. This will work. We will now have the oscilloscope display shifted by the offset of the battery, and this will work perfectly well. There's no problem with this. That is until there's a fault in one of the devices. And this is what makes this kind of fix workable, but it makes it really dangerous. And to see why this is a dangerous way to do it, we will assume that there's a fault in one of the devices. We'll start with the function generator, which is still properly grounded or properly earthed. We will assume that, first of all, we unplug everything. We'll assume that there's a fault in the power supply wiring here somewhere. Somehow, the live wire is now connected to the case. If we plug this in, we have power coming from the live wire through here, through this fault, into the case, and through the case to protective earth and back into the transformer. Now this will mean that either the RCD will trip, because now there's substantial current flowing through here, through live, but not coming back again through neutral, because it's going through the earthing wire, or the current might even be so high that the fuse or circuit breaker will trip, which is not drawn in here. But either way, something will shut off the power and give you a chance to remove the faulty device and correct the problem without any harm coming to you, the wiring, or the device. So this is very safe. But now assume we have this fault in the oscilloscope with the earthing wire removed. What happens here? Well, our electronics guy is standing here and maybe just wants to set something else on the oscilloscope. So he touches the oscilloscope case and zap! Power goes through live, through the fault, through the case, through the body, through the ground, into earth. Again, hopefully the RCD will trip here, but yeah, if not, you could be in for a nasty shock. And that's not just purely hypothetical. I've had this happen to me and I got a nasty electric shock of an improperly grounded device. So this can and will happen at some point. So this is why it's really dangerous to do it like this. Okay, but now I have my circuit like this, and I really want to measure this with the potential difference between those two sides. How can we do this without getting ourselves in danger? Well, first of all, let's remove those two lighting circuits. Not that they are dangerous. Well, this one is, but we'll just remove them to make some space here on the screen. And move the function generator over a little bit. And we unplug the oscilloscope. And we put in a new device. We put in an isolation transformer. And you notice that it's the same symbol as over here. And this is because both of them are transformers, only the isolation transformer is one you get to see, this one from the power company you don't get to see. And that the isolation transformer doesn't step the voltage up or down, it doesn't go from kilovolts to volts or something. It's exactly 1-to-1, 230 volts in, 230 volts out. But the reason why we do this is because now we have those two sides isolated. No power can flow from this side directly over here. So we plug the oscilloscope into the isolation transformer. And now we still have the question, what do we do with this earthing wire here? Well, we don't do anything. We just leave it hanging there. Or we plug it into the box which contains the isolation transformer, and in there it won't be electrically connected. So will it work? Yes, it will work, because as we can see, the earthing wires between those two devices are not connected. So we don't have a short in the battery, and the circuit will work as we've seen before. But now what will happen in case there's a fault? So let's assume we have the same fault as before. We have one of those wires touch the case of the oscilloscope. And now our electronics guy is again touching the case, and well, power can't really flow anywhere because it comes out from this side through the case to the body, but then it can't go back. So no circuit will be completed. Touching this is perfectly safe. And also it doesn't matter which side has this fault condition, as long as not both of them have the fault. And yeah, so that's why we use an isolation transformer. Now nothing can happen to you as you operate the device, and you can have any difference between those two grounds as you want.